Hey everyone, today we're looking at section 4.2. So this section here is talking about logarithmic functions and their applications. So remember how in the last section we had talked about exponential functions, and we said that exponential functions were one-to-one functions. So since exponential functions are one-to-one, it means that they are invertible, which means we can find their inverses. So in this section, we're actually studying the inverses of exponential functions, which will actually be your logarithmic function. So exponential functions and logarithmic functions are basically inverses of each other. Now, normally, when we talked about inverses in section 2.5, we had used this notation, F inverse, as the notation for our inverse functions. But in this case, we are actually going to use the logarithm notation instead of the inverse notation when we talk about the log functions. So our exponential function is of the form f of x equals a to the power of x. So its inverse function is actually going to be log of x with base a. So instead of using the f inverse notation, we're going to use this log notation for our base a. Exponential functions, the inverse will be log with the base a as its inverse function, okay? And the way you read this notation is log of x with base a, okay? All right, so let's take a look at this example over here. So looking at this exponential function, you have f of x equals 2 to the x. Now, if I replace that x with 3, I end up getting 2 to the third power, which is basically 2 multiplied into itself 3 times, right? So 2 times 2 is 4, 4 times 2 is 8, and that's where you get this answer, 8. Now, if we wanted to find the inverse for this pairing, right, that's where the log base 2 will come in. So you have log of x with base 2. So the way you write this is actually you have log of 8 with base 2 is going to equal 3. So we're basically saying log of 8 with base 2 is going to be the exponent that you basically raise your base 2 to get your number 8, right? So basically the idea is a log function is always going to give you the exponent that you need to get to this answer of 8. So basically you're asking 2 raised to what exponent gives us 8, and that's going to be the answer for your logarithmic function. So we're basically saying in general log of x with base a is the exponent that is used on the base a to obtain the value of x. So let's talk about our logarithmic function here. We have a positive constant a. A cannot equal 1. So basically we're saying your base a has to be a positive number and it cannot equal 1. And we will say the logarithmic function with base a is denoted by f of x equals log of x with base a, where you can actually say y equals log of x with base a if and only if a raised to the power of y gives you x. So you actually need to remember this relationship, because a lot of times we will need to take our log functions and rewrite it as our exponential function, and we may have to take exponential functions and rewrite them as our logarithmic function. So what happens here is the base a that you have on your log is going to be the same base a you have on your exponential function. So if you have log of base a over here, that's going to be the same thing as base a on our exponential function. Now in the logarithm, you have the value of x, which is next to the log with base a. That x is actually going to be the answer we get in our exponential form. And this exponent y that we raise our base a to is going to be the answer you get from your logarithmic function. So you need to remember the relationship between the log and the exponential function, because like I said, a lot of times we have to convert this from the logarithmic to the exponential form, and vice versa, so that we can solve some of these problems here. Okay, so they're asking us basically to solve these logarithmic functions here. So what's going to happen is we are going to have to rewrite these logarithmic functions into the exponential form to solve them. So again, remember the base that you have on the log 4 is going to be the same base you will have on your exponential function. And the way this works is we take this log with base 4. You're going to raise the exponent, which is going to be this value of y. So it becomes 4 raised to the power of y, which equals 1 over 16. So you actually have to start by rewriting your logarithm into the exponential form and then solving it from here forward. Okay, so let's take a look at how we can solve problem number 1. So again, remember, you're taking this base 4. This will become base 4 for our exponential function. Your logarithm is always equal to the exponent, so y is going to become our exponent on this base 4, and it will equal 1 over 16. And now we're actually going to use the one-to-one property of exponential functions to help us solve this. So the first thing I'm actually going to do is rewrite that 1 over 16, basically rewrite the number 16 as a base 4 number. So if you think about it, 16 is 4 times 4. So I can actually write this as 4 to the second power. So rewrite 16 as 4 to the second power. Now this is in the denominator, so of course we need to bring it to the numerator level. So it's 4 to the second power. When I bring it to the numerator level, it will become 4 to the negative second. Remember, your sign changes. And then same thing, just bring down your left hand side. And this is where the one-to-one function comes into play. So remember, we talked about this in section 4.1. If your bases are same on both sides, then by the one-to-one property, we can say x1 is equal to x2. So now that we have the same base 4 here, we can say y equals negative 2. And this is going to be our answer over here. So you end up getting log of 1 over 16 with base 4 equals negative 2. This is going to be your answer. Okay. All right, let's look at our next example here. So again, you are given log of 64 with base 2 equals y. So again, we need to rewrite this in exponential format. So this is base 2. That will be base 2 on our exponential form equal to y. So that y is our exponent. And this will equal 64. Okay. All right, so let's go ahead and solve this guy here. So again, rewrite this as 2 raised to the power of y equals 64. Now you have to think about how many 2's will need to multiply into itself to give us 64. So if you look at this, I have 2 times 2, which is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, which means I need one more 2 in there. 32 times 2 will be 64. So that's actually going to be 2 to the 6th power to give us this answer. So you will rewrite 64 as 2 to the 6th power. Okay. And then again, using our one-to-one property, I have base 2 and 2. So we can say y equals the number 6. And as you can see, once we convert this into our exponential form, it actually becomes very easy to solve these examples. Okay, so this is how you would go about solving number 2. Now let's look at number 3 over here. We are given log of 125 with 1/5 as our base, and that equals y. So again, we take our base 1/5. We're going to raise it to y as our exponent, and this will equal 125. Okay, so let's go ahead and see how we can solve this guy. So number 3 over here, we've got 1/5 raised to the value of y equals 125. Okay, now you can actually take that y and just put it on the 5 on the denominator, because 1 raised to any exponent will always be 1. So you can leave 1 as it is and just put that y on the 5 on the denominator. Here, 125 will break down into 5 times 5, which is 25. 25 times 5 is 125. So 125 is actually going to be 5 to the third power. So we can rewrite this guy as 5 to the third power. Now on the left hand side, since my 5 to the y is on the denominator, I want to bring it to the numerator. So when I bring it to the numerator, that exponent will become a negative exponent. And of course 5 to the third on the right hand side. So now that I have the same base of 5 on both sides, I can say negative y equals 3. And then go ahead and get rid of that negative on the y term. So the negatives cancel out, giving us y equals negative 3. Okay, so when we write this answer down, we will have log of 125 with the base of 1/5 equals negative 3. And that's what your logarithm would come out to be. Okay, so again, you can kind of see we're using that same technique here in problem numbers 2 and 3 to help us solve these logarithms here by converting them into exponential format. Okay? Alrighty, now remember, for the exponential functions, your domain was negative to positive infinity and range was going from 0 to infinity. So since the logarithmic functions are their inverses, that means your domain and range will switch places. So now for the logarithmic function, the domain will become 0 to infinity and the range will become negative to positive infinity. Okay, so since the domain for the logarithmic function is going from 0 to infinity, not including 0, that means you will have no logarithms of negative numbers or for the number 0. So there will be no logarithms for negative numbers or no logarithm for 0 either. If you try putting these in your calculator or solving them, log of negative 4 with base 2 or log of 0 with base 3, you're actually going to get an error message because these functions are undefined. Okay. Another thing you should note is that log of the number 1, which with any base a, doesn't matter what the base is, if you try to take log of the number 1, you're always going to get 0, because basically this will transform into base a with exponent 0, and we know that's the 0 exponent rule, and 0 exponent rule tells us all your values end up becoming 1. And again, this is true for any base a. Okay, so log of 1 is always going to be 0, doesn't matter what base you have on that logarithm. Okay, now for these logarithmic functions, there are actually two bases that we use most frequently, and those two bases are actually the base 10 and base e. So you will see that whenever we are using the base 10 logarithm, we actually, instead of writing that number 10, we just abbreviate it as log of x. So anytime you see log of x, it's understood that it's base 10, and we actually call the base 10 logarithm a common logarithm. And then our other commonly used or frequently used base is base e. So instead of writing it as logarithm with base e, we actually use this abbreviation ln, or as we call it, the natural log. So base 10 is called the common log, base e is called the natural log, and the abbreviation for base 10 is just log of x. The abbreviation for base e is ln of x, or natural log of x. And if you look on your calculators, you will actually see there are keys for both of these logarithms. So you will always have the natural log key and you will always have the common log key. Okay? So we can use that same definition for common log and natural log that we saw before. So if you have y equals log of x, that means, remember, this is base 10, so you can rewrite it as 10 to the exponent y equals x. For natural log, where you have y equals natural log of x, which is a base e logarithm, we can say e raised to the power of y equals x. So again, using that same relationship, but this time using it on common log and natural log. So let's take a look at what happens when we try to solve these examples over here. Okay, so again, you want to convert these into exponential form. So remember, when the base is not mentioned for the logarithm, it's understood it's base 10. So the way you rewrite this guy is actually going to be 10 raised to the power of y is going to equal 10 to the 6th power, just like we did in examples 1, 2, and 3. So here you will, since this is understood to be a base 10 logarithm, so when you write this, you will take this base 10, raise it to the power of y, and that will give you equal to 10 to the 6th here. Now since we have the same base 10 on both sides, we can say y equals 6, and you end up getting your answer. Log of 10 to the 6th is actually going to equal to number 6. Okay? Alright, let's look at number 5 over here. Again, this is understood to be base 10 whenever they give you just log by itself. So again, you are going to rewrite as 10 to the power of y equals 0.1. Now, you should know 0.1 is the same thing as 1 over 10, or the same thing as 10 raised to the power of negative 1. Because obviously, if this is 1 over 10, that 10 has an exponent of 1. So when we bring it to the numerator, that exponent will end up becoming negative, right? So you can rewrite this guy as 10 to the power of y equals 10 to the power of negative 1. So since I have the same base 10 again on both sides, I can basically say y equals negative 1. So when we write our logarithm, it will become log of 0.1 equals negative 1. Okay? Now we are moving to natural log. So remember, with natural log, when no base is mentioned, it's understood that it's base e. So that means you're going to take this base e, raise it to the power of y, and that's going to equal this value of e. Now since there's no exponent on this e on the right hand side, it's understood that that exponent will be 1. So since I have the same base e on both sides, we can basically say y equals 1, right? Using that 1-to-1 property again. So now we can say natural log of e equals 1. That will be our answer. Same thing in number 7. This is again a natural log, which means it's understood it's a base e logarithm. So again, you can say this base e to the y value is going to equal what you have here in the parentheses, which is e to the negative 5. So again, since I have the same base e on both sides, by 1-to-1 property, we can say y equals negative 5. And you can rewrite this logarithm as natural log of e to the negative 5 equals negative 5. Okay? Alrighty, and then that brings us to this last one here, which is natural log of negative 6. Now, natural log of -6, again, if you try to think about it, we know this is base e. They didn't really tell us, but you can think it equals y. So you are saying e to the power of y equals -6. But there's really no base e on this side, right? We just have the number -6. Now, if you actually go back and look at what we just talked about here, we said there are no logarithms of negative numbers or 0. So this will actually fail right here. Now, even if you try to plug in this natural log of -6 in your calculator, you are actually going to get an error message on your calculator, and that's because -6 is not in the domain of our logarithmic function. So you're actually going to get that this is undefined, and that's because -6 is not in the domain of our natural log function. Okay, so not in the domain of the natural logarithmic function. So this does not work out. You will find no value of y which will satisfy this equation, so it's undefined. Now, one thing I want you to notice before we move on from here, so you know what happens here is anytime this base and this base match, your answer is always going to be what this exponent is. So you will see our answer came out to be that number 6, which was our exponent on 10 to the 6th. If you look at number 5, our base here is 10. 0.1 is the same thing as 10 to the power of -1. So basically, if you have log of 10 to the power of -1, and this is already a base 10 logarithm, your answer is going to be -1, which is what we got over here. If you look at number 6, our logarithm is a base e function, and you also have base e here in your parentheses, which is raised to the first power, and you can see that's the answer we got. You get 1 as your answer. So anytime this base here and this base here matches, your answer is always going to be that exponent. And we are actually going to take a look at these rules later on, but since we are working through these examples right now, I just wanted you to notice that anytime your bases match, the answer is going to be that exponent that you have. Okay? Alrighty, so this was our examples for common log and natural log. Now let's talk about the graphs of logarithmic functions. Now, of course, we know these guys are inverses of our exponential functions. So basically, the graphs for an exponential function with its logarithmic function are going to be reflections of each other with respect to the line y equals x. So basically, the graph of your logarithm will be a reflection of the graph of your exponential function. Okay? Now, if you go back and look at the characteristics that we had talked about for our exponential function, you should remember that our exponential function has a horizontal asymptote at the x-axis. So that will end up becoming a vertical asymptote at the y-axis for your logarithmic function. So the horizontal asymptote at the x-axis will become the vertical asymptote at the y-axis from the exponential to the logarithmic function. All right, so let's take a look at the graph of f of x equals log of x with the base 6, and then they want us to find the domain and range. So you know what happens is when we actually try to graph these logarithmic functions, you actually start out by graphing your exponential function. So you graph your exponential function, create your x and y table, and then what we do is we switch the x and y table from the exponential function to get our logarithmic function. And that's actually how you end up graphing these log functions is first by starting with the graph of the inverse function, which will be the exponential function here. So the first thing we are going to do is actually graph. Let's create a table for our exponential function. So we can use the values -2, -1, 0, 1, and 2 in this function over here. Okay, so 6 raised to the power of -2 will actually end up giving you 1 over 36, which will be approximately 0.0278. 6 raised to the power of -1 will become 1 over 6, which will be approximately 0.1667. 6 raised to the power of 0 will of course become 1. 6 raised to the power of 1 is 6. 6 raised to the power of 2 is 36. So this will be our table for the exponential function. And then we can basically switch our x and y values to get the table for our logarithmic function. So now my x values here will become 1 over 36, 1 over 6, 0, 6, and 36. And our y values will become -2, -1, 0, 1, and 2. So we're literally just switching our x and y tables from the exponential function to the logarithmic function. And then remember we talked about using the line y equals x as our line of reflection. So we can go ahead and draw that line just so that we can see what our graph's reflections will look like. Okay, so this will be the line y equals x. So I'm actually going to graph my 6 to the x exponential function first. So that's going to be at 0, 1, 1, and 6. And then these guys would be getting closer to the x-axis. So this graph will get closer here. This one will go up. And this is for y equals 6 to the x. So remember, this is an increasing function. Okay, we have y-intercept at 0, 1. We have horizontal asymptote at the x-axis, which is the line y equals 0. Okay. Domain for this function is going to be -infinity to +infinity, and range is going to be from 0 to infinity, not including 0. So that's for our exponential function. Now when we draw its reflection, we'll use the second table over here. So oh, I just realized my error over here. This should be the number 1. Okay, so I should have 1, 0, 6, 1, and then let's see, these guys here would be getting closer to -1, -2. So this line will actually start going down this way, and then this part of the graph will go along like this. So this is going to be our log of x with the base 6 function. So again, as we go from left to right, our y values are getting larger, so we still have an increasing function. But now, instead of a y-intercept, we are actually having an x-intercept at this point, 1, 0. Instead of having a horizontal asymptote, we have a vertical asymptote at the y-axis, which is going to be the line x equals 0. The domain of our function, since we have a asymptote at the y-axis, That means we cannot include 0. And then, of course, on the right-hand side, we are going to positive infinity. And your range, of course, you can see the left arm of our graph is going down towards negative infinity. And the right arm, as it goes right, will also go up. So that's going towards positive infinity. So your domain and range will switch values from the exponential function to the logarithmic function. Now, if you look at this line, y equals x, that dotted line in the middle, the idea is if I were to fold my graph along that dotted line for y equals x, my two graphs would coincide, right? They would overlap. So that's how you can tell they are reflections of each other. Okay, so this is kind of the idea behind graphing logarithmic functions when you're doing these graphs by hand. You graph the exponential function first, and then reversing your x and y table, you then graph your logarithmic function. Okay? Okay. So again, you should notice that our function is 1-to-1. It will pass the horizontal line test. So if I were to draw a horizontal line through my logarithmic graph, it would only cross at one point. So we know that function is 1-to-1 because obviously it has an inverse function. It's an increasing function. We talked about that. Okay. And here, they're actually just showing you what the graphs of your common log and natural log would look like. So of course, you know those are base 10 and base e functions. So of course, you can see both of these functions are also increasing functions. They are both crossing at the same x-intercept point, which is 1, 0. They both have vertical asymptote at the y-axis, so it will get really close to the y-axis, but it will never touch and never cross that line, right? So a lot of the similar properties that you saw here with this logarithm with base 6 function, you will see a lot of those similar characteristics with your common log and natural log. Okay, so just like with exponential functions, if this base a is a number greater than 1, then your function will be increasing. If your base a is a number between 0 and 1, then your function will be decreasing. So that's what we're going to be doing here in number 10, is talking about how the graph of log of x with base 1/6 is going to end up looking like. So let's take a look at this graph here. So just like we did before, we'll go ahead and do a table for the exponential function, which will be 1/6 to the x power. Okay, so using again -2, -1, 0, 1, and 2, we will actually end up getting 36 for this guy, 6 for this guy. This will be 1. This will be 1/6, which will be approximately 0.1667, and this will be 1 over 36, which will be approximately 0.0278. To find our table for the logarithmic function, you just switch your x and y values here. So now these guys will be -2, -1, 0, 1, and 2, and these guys will be 36, 6, 1, 1/6 for this guy, and 1 over 36 for this guy. Okay, again, I'm going to draw my y equals x line so we know what that reflection will look like. Okay, so again, I'm going to start with the graph of my exponential function. So that's going to be at 0, 1. At -1, I am at 6. At +1, I'm at 1/6. +2, I'm getting closer. So obviously we know this is going to be a decreasing function because we saw that in section 4.1. And this guy will go up like this. So this is the graph for our y equals 1/6x. Okay, so we should notice that this is a decreasing function. We still have y-intercept at the point 0, 1, horizontal asymptote at the x-axis, which is the line y equals 0. Let's see, domain is still going to be all real numbers, and range is going to go from 0 to infinity, not including 0, right? Because of that horizontal asymptote. Okay, now let's look at the graph for our logarithmic function. So at positive 6, we are at negative 1. Okay, at 1, 0. For positive 1, we are at 1, 6. Okay, so graph will look something like this. This part will go here, and then this part will be getting closer and closer to the y-axis. So this is our log of x with a base 1/6. So again, you should notice as we go from left to right, this is a decreasing function. We have x-intercept in this case at the point 1, 0. Instead of a horizontal asymptote, we have a vertical asymptote at the y-axis, which will be the line x equals 0. And our domain is going to go from 0 to infinity, not including 0. Because again, at 0, you have your vertical asymptote, and then range will be negative to positive infinity. So some of these properties are still staying the same, but one of the main things you should notice is that you have a decreasing function instead of an increasing function like we had in the previous example. Okay, so this was our graph for number 10. So again, they're just talking about some of these properties here for our logarithmic functions. So like I said, when your base is greater than 1, the function is increasing. When the base is between 0 and 1, the function is decreasing. The x-intercept for our graph is going to be at the point 1, 0. We have a vertical asymptote for our graph at the y-axis. Domain is going to be 0 to infinity. Range is negative infinity to positive infinity. And again, remember, in domain, you're not including 0. Our function is definitely 1 to 1. And then you should notice that the log function is the inverse for the exponential function. Because again, if you look at this graph over here, if I fold my graph along that line, the dotted line y equals x, my two halves will actually coincide. So they will overlap when I fold it along that line, okay? And that's going to be true for all inverse functions, okay? So I do want to talk about what happens with transformation here. So when you're looking at logarithmic family of functions, so again, this variable b tells you if your function is going to stretch or shrink. So if the value of b is greater than 1, your function will stretch. If the value of b is between 0 and 1, your function will shrink. If you put a negative on the value of b, that means you're creating a reflection of your function in the x-axis. Okay, and then this value of h here, if h itself is a positive number, your graph will move to the right. If h itself is a negative number, your graph will move to the left. For this value of k, if k is positive, the graph moves up. If k is negative, your graph moves down. So same thing we saw with transformation of functions in chapter 2, and of course the same thing we saw in 4.1 with our exponential function. So still going to have a lot of the similar properties. So if you look at number 11 over here, what transformation values are you seeing over here? We've of course got this -3. We've got this number 2 here. So what kind of movement is our graph doing? Do we have a reflection? Do we have a stretching or a shrinking? Is the graph moving up or down? Is the graph moving left or right? So take a second and think about this. If you want to pause the video, you can. And then when you think you know what kind of transformation we are seeing, you can come back and restart the video again. So the one thing you should notice here as you are going through this, you have -3 plus log of x plus 2. Now this x plus 2 inside the parentheses is definitely coming from your x minus h here. So the x plus 2 is actually telling you it's x minus -2. It's the two negatives which is making this a positive, right? So this is going to be our h value, and since this h value is less than 0, that means we are actually moving left by 2 units. Okay, so that's the movement that's happening here. Now with this -3, because you have a plus sign in the middle between the log and the -3, you're actually looking at the k value. This -3 is not the b value, because if this was b, you would have had a multiplication sign here instead of having an addition sign. So since that's an addition sign, that means this -3 is your k value. And since this is a negative number, that actually tells us our graph is moving downward by 3 units. So our graph is actually moving to the left by 2 units and moving down by 3 units. So that's actually the transformation that's happening here in number 11. So let's go ahead and take a look at number 11 over here and how the transformation will work. So what you can actually do is you can start by creating a table for just the original function, which would be log of x. Now you will notice there is no base mentioned on the log function, right? So when there is no base mentioned on the log function, that actually means you are looking at a base 10 function here. Now, if you wanted to create a table for the base 10 function, you can always start by creating a table, and I'm going to do this down here. You can always create a table for the exponential function 10 to the x, and then use those values to come up with your table for log of x. So this would end up becoming 1 over 100, which would be 0.01. This would become 1 over 10, which would be 0.1. This would be just number 1 because that's your zero exponent rule. This would be 10, and this would be 100. So if you just reverse this table, I would have -2, -1, 0, 1, and 2 here. I would have 0.01, 0.1, 1, 10, and 100 over here. So this would be your table for the basic log of x function, but now to create the table for our function over here. Oops. What you would actually need to do is the x values. Remember, these numbers were moving to the left, so to all the x values, you would need to subtract them by 2, and all the y values, you would need to subtract them by 3 to create your table for this transformation function. So take each one of your x values here in this table for the log of x and subtract each one of them by 2. So 0.01 subtracted by 2 will give you -1.99. 0.1, again I'm looking at my log of x table, 0.1 minus 2 will give you negative 1.9. 1 minus 2 will of course give you negative 1. 10 minus 2 will be 8. 100 minus 2 would be 98, right? And then on our log of x function, from all of these y values, we will be subtracting 3. So you're going to do negative 2 minus 3, which will give us negative 5. Negative 1 minus 3 will be negative 4. 0 minus 3 is negative 3. 1 minus 3 is negative 2. And then, of course, 2 minus 3 is negative 1. Okay, so this is how you actually come up with the table for our transformation function. And let's see what kind of graph this will look like. So let's graph this guy. So I've got negative 1.99, which is almost negative 2, and that's going to be at negative 5. So this would be somewhere over here. For negative 1.9, we are at negative 4, so just a hair inside, we're going to be at negative 4. I am at negative 1 and negative 3. At positive 8, I am at negative 2. Okay, so remember what happened. Our graph moved 2 units to the left. So that means your vertical asymptote, which would normally be at the y-axis, has actually now moved 2 units to the left. So you're actually going to have a vertical asymptote right here, which means this part of our graph is going to get really, really close to this line for the vertical asymptote. Okay, now our graph also moved 3 units down. Okay, so what we actually need before we can complete this graph is we need to know where is our graph crossing the y-axis at. So you're actually going to put your x value as 0 into this function, negative 3 plus log of x plus 2. Put that in your calculator and find out an approximate answer for where our graph will be crossing the x-axis at, and this should come out to be approximately negative 2.699. So negative 2.699, and again this will just be an approximate location. So now we can kind of see where our graph would be going here. Okay, so something like this, and this is our graph for our transformation function. Okay. So obviously this is still an increasing function, right? We have our vertical asymptote, which got moved to the left by 2 units since our graph moved left to the 2 units. So it's actually going to be at the line x equals negative 2. And then you can kind of calculate where your x-intercept will be, but you don't really have to worry about that right now. Now let's talk about the domain and range. So again, your domain, instead of starting at 0, has also moved to the left by 2 units. So you're actually now looking at a domain going from negative 2 to infinity, right? But your range, even though our graph moved down by 3 units, it did not affect our range because we are still looking at negative infinity to positive infinity for our range value. So I hope you can kind of see how your transformation works with a logarithmic function over here. Okay? Alrighty. Now let's talk about looking at how we can use logarithms to solve exponential functions, or how we can use exponential functions to solve our logarithmic functions. So they are saying some equations involving logs can be solved by writing an equivalent exponential function, and then in that same way, some equations involving exponents can be solved by writing them as equivalent logarithmic equations. So let's take a look at number 12 over here. So we are given log of w with base 4 equals 7. So remember our conversion. So when you are given log of x with base a equals y, that ends up becoming a raised to the value of y equals x. So using that same notation, we will rewrite this guy as 4 raised to the power of 7 equals w, and then you can just plug this into your calculator to find out what 4 raised to the power of 7 is. Okay, so this will come out to be 16,384 once you put it in your calculator. Okay, so this was number 12. Now let's look at number 13 here. They're asking us to find the inverse for this function f of x equals 3 times e raised to the power of 5x minus 1. So let's go ahead and take a look at this example over here. Okay, so we are given the function f of x equals 3 times e to the power of f of x minus 1. Now they're asking us to find the inverse function. So of course this guy is our exponential function, which means its inverse function is going to be a logarithm, right? But to get to that answer, you actually have to use the switch and solve method we had seen in section 2.5. Okay, so the first thing we're going to do is rewrite f of x as y. And then remember, in the switch and solve method is where we interchange our x and y variables. So the y will become x and the x will become y. And now the idea is we want to try and get that y by itself. Okay, so the first thing we're actually going to do is get rid of that 3. So since we're multiplying 3 into that base e, to get rid of it, we divide both sides by that number 3. So you can leave it as x over 3, or normally I just write that as 1/3 x will equal e raised to the power of 5y minus 1. Now, if you remember, when we were doing these examples here, I had talked about how when your base and the base inside your parentheses are the same, the answer is always going to equal the exponent. So kind of like what we did in number 4, what we did in number 7, you can kind of look at those examples. So what we're actually going to do here is to simplify that right hand side, we're going to go ahead and take a natural log on both sides of our equation, and we are doing this because natural log also has base e, and this right hand side exponential function is also base e, right? So since they are both base e, you will end up by using that explanation we did back in example 7 for that matter, these guys will end up giving us 5y minus 1 as our answer, and then this side will basically just stay as 1/3 x inside that natural log. Okay, and then all you have to do is get that y by itself, so we can start by adding 1. So this guy will cancel out. You end up getting natural log of 1/3 x. The plus 1 is on the outside, and then we are just left with 5y, and then to get rid of that 5, we divide both sides by 5, and you end up getting y by itself, And this one here, you can write it as 1/5 natural log of 1/3 x plus 1/5. And then the last thing to do, or if you didn't want to break it up like this, you can just put 1/5 on the outside, and then you can say natural log of 1/3 x plus 1. You can write it this way also. So whichever one you like the best, you can write it either way. And then the last thing to do is rewrite that y as our f inverse notation. Okay? And then that would be, again, whichever form you want to write this as. And this is how you would actually convert this exponential function into its inverse, which would be a logarithmic function. So either this, or you can also have it in this format. So whichever one you, as I said, you want to leave it in. So either this or this. Okay? So that's kind of how we can rewrite logarithms into exponential functions, or exponential functions into logarithmic functions, which is what we did here. Okay. Now, just like we had used the one-to-one property of exponential functions to solve exponential equations, you can use the one-to-one property of logarithmic functions also to solve the logarithmic equations. Okay. So basically, the one-to-one property says that if two quantities have the same base a logarithm, then you can basically say those two quantities are equal to each other. So if you have log of base a here and log of base a here with values of x1 and x2, so we can basically say if both the logarithms have the same base, then x1 is going to equal x2. Okay? But that treatment is going to be a little bit different when we work through these examples. So let's take a look at how we can try and solve some of these logarithmic equations. For some of them, it may actually be easier to convert them into exponential format and then solve it from there. So let's take a look at these examples and see what we come up with. So we've got number 14 over here, which is log of 2x with base 5 equals -3. So I'm actually going to convert this into its exponential notation. So again, just to remind you of how to do that. So we have base a raised to the exponent of y equals x. So this is how we rewrite it. So this guy will become base 5 raised to the exponent of -3 equals 2x. So since I have 5 to the -3rds, I can make that into a positive exponent by rewriting it as 1 over 5 to the thirds, and that equals 2x. Now when you multiply 5 times 5 times 5 into itself, you should end up getting 125. So this will become 1 over 125, and then you've got 2x on the other side. Now you can either divide this by 2, or you can think of multiplying both sides by 1/2, which is the same thing, because my 2 and 2 will cancel out here. I'm left with x here, and when I multiply this, I get 1 over 250 as my x value. So that's that x value you have inside the parentheses. So this is how you would go about solving something like number 14 over here by converting it into its exponential notation. Okay? So we've got a couple more examples to work through this. So let's go ahead and look at all of these examples from 15 through 18, and let's see how we solve each one of these individually. Okay, so let's look at number 15 over here. We are given log of x with base 3 equals 1/2. So again, in this case, you can convert this into the exponential notation. So this will be 3 raised to the power of 1/2 equals x. So when we are trying to solve this, 3 to the power of 1/2, remember that exponent of 1/2 is the same thing as a square root, so this will actually end up becoming square root of 3, which equals x. And most of the time they will want an exact answer, so you can actually just leave it as it is. If they say convert it to a decimal approximation, then you can put the square root of 3 in your calculator and see what you come up with. So again, we take that 3, raise it to the power of 1/2, set it equal to x, and 3 raised to the power of 1/2 is the same thing as square root of 3, and this will be our answer for number 15, and that's really it. That's all you have to do there. So that's number 15. Now let's take a look at number 16. So for number 16, we are actually given 3 to the power of x equals 77, and they're asking us to find the value of x. So again, just to show you how the conversion works, okay, so we are given this in the exponential notation, so we're actually going to put it in our logarithmic form. So this would be logarithm. It will have the same base as base 3 over here, but this will be log of the number 77 at base 3 equals x. Remember, your logarithm always equals the exponent. Now, we're not quite ready to see how to solve this log of 77 with base 3. We will talk about that in the next section, but there is a way that you can solve this and get an answer. But basically the idea is that you have actually an irrational number as your solution here. So this is going to be an irrational number, but when we are ready in the next section, we'll talk about how to solve this. So for now, for this section, just leave it as log of 77 with base 3 as your exact answer for number 16, okay? Okay, let's look at number 17 here. You are given 10 to the power of x equals 25. So again, we're going to convert this from exponential into logarithmic form. So this will be log, which will have a base 10, same as our exponential. And this will be log of the number 25, which equals x. Okay, now remember, log with base 10 is our common log. So you actually don't have to write that base 10. You can just rewrite this guy as log of 25 equals x. Now, if they want an exact answer, you stop right here. If they say they want a decimal approximation, then you can calculate log of 25 on your calculator. Otherwise, just leave it as it is. The exact answer would be log of 25. Okay? And then the last one in this set was number 18, which is e raised to the power of 2x equals 3. So again, we're going to rewrite this in the logarithmic form. So this will be log of base e, right, at the number 3, and this will equal the exponent 2x. So again, take this base e, and that will become the same thing as log of base e of number 3 equals 2x. Now remember, we don't really write it as base e logarithm, right? We actually rewrite this guy as natural log of 3 equals 2x, and then to get x by itself, you can divide both sides by 2, or basically multiply both sides by 1/2. So the 2 and 2 will cancel each other out, giving us 1/2 natural log of 3 equals x. Again, if they want an exact answer, stop right here. If they want a decimal approximation, then you can throw this into your calculator. Okay? So remember, we never leave log of base 10 with base 10. You always make it just log of whatever number is. Same thing with natural log. We never leave it as log with base e. We always write it as natural log of x. So that's basically what we did in example 17 and 18 over here. Okay, so this will be our answer for problem number 18. Okay. They're basically saying you have a function gallery on your textbook pages if you want to take a look at those. But the very last example that we have here is where we want to talk about this application. So they are saying how long does it take for $4 to grow to $12 at 5% compounded continuously. So that means the $4 is the money that we first invested. So that's going to be our principal. It's going to grow to $12, which means that's my future amount. So that's our A value. 5% of course is our annual interest rate. So remember, we always convert our percents into decimals. When they're saying compounded continuously, this is where we use our first formula, right? Is that going to have that base E as part of its calculation? And they're actually saying how long does it take, which means they're actually asking us to find the time, t, so that's going to be in our exponent. And since the time t we're trying to find is in our exponent, that's why we will actually need to use logarithms to help us solve this application. Okay, so let's go ahead and take a look at how we can solve number 19. Okay, so I've already got all of this written down. Our principal is $4. Our future value will be $12. This is at an interest rate of 5%, so that's 0.05, and we're finding the time t. So plug all of these values into your formula here. So our A is 12. Our principal is $4, and that's going to be multiplied by E raised to the exponent of 0.05 multiplied by t, right? And we don't know what t is at this moment. So the first thing we want to do is isolate that E with its exponent of 0.05 multiplied by t. So the first thing we're going to do is divide both sides by this number 4 so that we can get E by itself. And of course 12 divided by 4 will give you 3. This will be E raised to the power of 0.05 t. Now, since my t is in the exponent, we won't be able to do anything, so we need to bring that t down to the base level before we can find it. So the idea is we actually need to get rid of this base E, and the only way we can do that is base E means we have to use a natural log, because natural log also has a base E on it. So that means you actually take a natural log on both sides of your equation. Okay, so the left hand side will of course just stay as it is, natural log of 3. But the right hand side, since natural log has a base E and my exponential function also has a base E, they will basically get rid of each other, giving us 0.05 t, which makes it come down from the exponential level to the base level. And then of course it makes it very easy for us to find the value of t, right? Because now that it's come down to the base level, all we have to do is divide both sides by this 0.05 to get t by itself. And now you can just put this in your calculator. So just type in natural log of 3 divided by 0.05. Just make sure if your calculator opens a parentheses for natural log, make sure you close that parentheses after 3 before you do the division with 0.05. So when you put this in your calculator, you will actually get an approximate answer, because you will get a pretty long value over here. So just rounding this to 2 decimal places will come out to be approximately 21.97. But if you want to round it up to a whole number, you can actually say this is going to be approximately 22. And of course time is always in years. So we are saying for our money to grow from $4 to $12 at an interest rate of 5%, it's actually going to take 22 years. Now your money is growing by 3 times, right? And that's really good. You're just looking at smaller dollar values, but you know, if this was $10,000, then in 22 years, this would have gone up to 3 times, which would be $30,000, right? So it's just, we are saying it's going to grow by threefold in 22 years. So this is how you would go about solving this example over here. Okay, so like I said, we would not have been able to do this till we had talked about logarithms. Okay, so this was our example 19, and this was the last example we had here in section 4.2. So again, look through these notes, look through the video, let me know if you have any questions. We'll do a couple more examples in class, and I'll answer any questions that you guys have, okay? So have a wonderful day, guys. I will see you in class. Be careful, be safe, and talk to you later. Bye-bye.